Cool. So I thought it was a good, it was worth diving a little bit more into eigenvectors and eigenvalues because I think it's sort of popping up more often than not. And then also when it comes to everything that's related to quantum machine learning, as those are things which are definitely a mass known concept for machine learning anyway. From a classical perspective, I think that definitely makes sense. And I know I've done that already, just really roughly using Wikipedia some videos ago, but I think, and I'll probably keep doing that as well. I just want to go through these and see. So I got an intuitive sense in terms of how this all plays along, and sort of being eigenvectors and eigenvalues, sort of ways to describe a matrix, or sort of ways to construct a matrix, maybe. Um, I don't know. Let's just go through this quickly. Maybe it's useless for you, so just keep the video. But uh, I think it kind of deserves a bit of a detour at least. So, good. Let's go ahead. Some concepts live in the heart of data science. Eigenvectors are the concepts. The article will aim to explain what eigenvectors are, how calculated, and use them. Okay. So, quick introduction. Every vector has a direction when it's plotted on an XY chart. Eigenvectors are those vectors when a linear transformation is performed on them, then their direction does not change. This attribute of eigenvectors make them very valuable, as I will explain in this article. Eigenvalue, the scalar that is used to transform an eigenvector. Eigenvectors and eigenvalues are used to reduce noise in data. They help us in proficiency in computationally intensive tasks. They also eliminate features that have strong correlation between them. And also help in reducing overfitting. So, brief introduction. How are they calculated? That can be interesting to sort of see the inner workings of that, and I'll then present a working example. Okay, let's see. It will build our confidence in dimension reduction techniques, which are crucial to understanding data science. So, when we're building forecasting models that are trained on images, sound, and or textual contents, then the input feature sets can end up having a large set of features. It is also difficult to understand and visualize data with more than 3 dimensions. As a result, we often use one-hot encoding to transform values in textual features to separate numerical columns. Their importance in linear differential equations when you want to find a rate of change, or when you think of eigenvalues and eigenvectors. Okay, so that's kind of like, yeah, that's one of those things that I was kind of suspecting, right? Providing a summary of a large matrix. So it can represent a large set of information in a matrix. One eigenvalue and eigenvector is used to capture key information that is stored in a large matrix. But I think it's not all the information. So, right, because as far as I know, there are there's a set of eigenvectors, eigenvalues of a matrix, and their eigenvectors. Performing computations on a large matrix is a very slow process. To elaborate, one of the key methodologies to proficiency is to reduce the dimensions after ensuring most of the key information is maintained. I guess maybe one of the ways you reduce dimensions is by finding those eigenvector, an eigenvector and an eigenvalue, and just removing them from the matrix. Maybe. A component analysis is PCA. I wanted to touch base on that as well with quantum computing in focus, because it's one of the points in the O'Reilly book, which I haven't read that part yet. Sort of quantum PCA. But we'll see. That's definitely another set of videos. A component analysis is one of the key strategies that is utilized to reduce dimension space without losing valuable information. Additionally, eigenvectors and eigenvalues are used in facial recognition techniques such as eigenfaces. Really convenient naming. It is now apparent that eigenvalues and eigenvectors are one core concepts to understand. Practical usages, increasing compressed data. So, more use cases. Occasionally, we gather data contains a large amount of noise. Finding important, meaningful patterns within the data can be extremely difficult. Eigenvectors and values can be used to construct spectral clustering. We can also use eigenvectors to rank items in a data set. I mean, I don't know. So far, it's just trying to justify why this is important. Eigenvectors are used to make linear transformations understandable. Maybe from a transformation perspective, that's kind of what maps the closest to quantum computing. Think of eigenvectors as stretching, compressing an XY line chart without changing its direction. Eigenvectors and eigenvalues revolve around the concept of matrices. Matrices are used in machine learning problems to represent a large set of information. Eigenvalues and eigenvectors is about constructing one vector with one value to represent a large matrix. Okay, so it basically it's sort of another way to represent the information in a matrix. Let's quickly recap and refresh how matrix multiplication and addition works before. So that's addition. So you've got like A and J. So A plus J is here, and then repeat that. Multiplying a scalar with a matrix, you get the scalar and you multiply it through all the different components. Matrices multiplication. Yeah, so that's basically these times these, right? Times is like you multiply each of those components and add them all together, and then that gives you this row in here, and then you do the same for the other ones. Okay. Let's utilize the knowledge about, okay, although we don't have to calculate the eigenvalues and eigenvectors by hand every time, but it is important to understand the inner workings to be able to confidently use the algorithms. Key concepts. Eigenvalues and eigenvectors have the following components. A matrix has the size of x rows and y columns. A square matrix is one which has the size of n, implying that x and y are equal. A square matrix is represented as A. This is an example of the square matrix. Yeah. The eigenvector is an array with n entries, where n is the number of rows or columns of a square matrix. The eigenvector is represented as x. Does it mean eigenvectors only exist in square matrices? The eigenvector is represented as x. Okay. Keynote: the direction of an eigenvector does not change when a linear transformation is applied to it. Therefore, eigenvector should be a non-null vector. Now, eigenvalues. We are required to find a number of values known as eigenvalues such that, okay, a times x minus lambda times x equals 0. Okay, x being the vector, right? Because that sort of seems to imply that a equals lambda, right? Lambda. Kind of. So, but lambda being a scalar, so being a number, not a matrix. So you're looking for a number that is representative of the information of the matrix. And so this way you kind of compress that information. Yeah, makes sense. Eigenvalues are represented as lambda. The above equation states that we need to multiply a scalar lambda to the vector x such that it is equal to the linear transformation of matrix A once it's scaled by vector x, eigenvector. Keynote: the above equation should not be invertible. The determinant should not be invertible. The determinant of a matrix is a number that is computed from a square matrix. It is basic arithmetic where the diagonal elements are multiplied by each other and then they are subtracted together. As the above equation should not be invertible, we need to ensure that the determinant of the matrix is 0. Last component, identity matrix. A square matrix which has 1 as a diagonal and all of the elements 0 is known as identity matrix. Okay. Yeah. So you can then do it this way. Yeah. Yeah, you can, of course, this, and then additionally determinant. What's the determinant of a matrix? Just give me a second. Determinant of matrix. I just have it open on another tab. It's a special number that can be calculated from a square matrix. So it's 3 times 6. Okay. This is vertical lines, yeah. So just to quickly show you what I'm looking at. So this is basically the determinant of A equals A times D minus B times C. Okay. Let's go back to this. So this thing with the should not be invertible. It's something that I don't fully understand why, but let's go ahead. So how to calculate the eigenvalue for matrix A of size n, find eigenvalues of size n. The aim is to find eigenvector and eigenvalues of A such that A times eigenvector minus eigenvalue times eigenvector equals 0. Find lambda such that determinant A minus lambda times the identity A equals 0. A lambda times identity is this. If A is this, then A minus lambda times identity is this. Finally, calculate the determinant of that. Once we solve the equation above, we'll get the values of lambda. These values are the eigenvalues. Okay. How to calculate eigenvector? Okay, so okay, yeah, but now we have the keys. It's time to compute the eigenvector together with me. Okay, but that's just eigenvectors together, calculate in Python. Summary. This article briefly explains one of the key areas of machine learning. It started by giving a brief introduction to eigenvectors and eigenvalues. That is, explain how eigenvectors and eigenvalues are calculated from the foundations of matrix multiplication. In addition, that we can understand the key components thoroughly. Yeah, but that still doesn't. It's not what I expected. I thought it would be more like, how do they relate? Yeah, but I mean, what else? What else can be in there? I mean, let's look at it from where are the source definition? No, this is not definition. Eigenvector is an array with n entries where n is the number of rows or columns. Okay, the eigenvector is represented as x. So you want that. So the eigenvector. So you're literally are looking for lambdas and vectors that kind of basically represent the same information than the matrix. The above equation should not be invertible. The determinant of a matrix is a number that is computed from a square matrix. It is basic arithmetic where the diagonal elements are multiplied by each other and then they are subtracted together. As the above equation should not be invertible. Why should not be invertible? That's what's not clear. Okay. Eigenvectors and eigenvalues applications in chemistry, for example, because that's what's interesting. Okay. Quora. So that we're back to the Wikipedia entry. In linear algebra, an eigenvector or characteristic vector is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. There is a direct correspondence between n by n square matrices and linear transformations from an n-dimensional vector space into itself. Given any basis of the vector space, for this reason, in a finite dimensional vector space, it is equivalent to define eigenvalues and eigenvectors using either the language of matrices or the language of linear transformations. Okay, so what this basically says at the intuitive level is that in the case of n by n matrices, you can understand transformations in this n-dimensional space by just drawing a matrix, but as well as just in the form of linear transformations, meaning vectors and scalars. So what do we have here? History, algebraic multiplicity, calculation applications. Molecular orbitals. stress tensor graphs. In quantum mechanics, in particular in atomic and molecular physics within the Hartree-Fock theory, the atomic and molecular orbitals can be defined by the eigenvectors of the Fock operator. The corresponding eigenvalues are interpreted as ionization potentials via Kopman's theorem. In this case, the term eigenvector is used in somewhat more general meaning, since the Fock operator is explicitly dependent on the orbitals of the eigenvalues. Thus, if one wants to underline this aspect, one speaks of nonlinear eigenvalue problems such as Schrodinger's equation. An example of an eigenvalue equation where the transformation T is represented in terms of a differential operator is a time-independent Schrodinger's equation in quantum mechanics, where H is Hamiltonian, where H, the Hamiltonian, is a second-order differential operator. The wave function, and the wave function is one of its eigenfunctions corresponding to the eigenvalue E, interpreted as its energy. So basically this is. So I think it's. So basically, what this is saying is that the wave function that describes a particle or a system is one of its eigenfunctions corresponding to the eigenvalue E, being the energy. However, in this case, where one is interested only in the bound state solutions of the Schrödinger equation, one looks for these within the space of square integrable functions. Since this space is a Hilbert space with a well-defined scalar product, one can introduce a basis set in which it can be represented as a one-dimensional array, a vector, and a matrix respectively. This allows one to represent the Schrödinger's equation in a matrix form. The bracket notation is often used in this context. A vector which represents a state of the system in the Hilbert space of squared integral functions is represented by this. In this notation, the Schrödinger's equation is where this is an eigenstate of H and E represents the eigenvalue. H is an observable self-adjoint operator. The infinite-dimensional analog of Hermitian matrices, as in the matrix equation above, is understood to be the vector obtained by application of the transformation H to these. Okay. So I see kind of where this is going in this sense that I mean, of course, none of this makes sense to me, sort of, from a clarity perspective. I don't really understand the details, but it's like, it happens to be that the way the energies and the Hamiltonians are defined, it's the same as the eigenstate, the eigenvectors and eigenvalues. So okay. Quantum mechanics, yeah, that's what I read already. I'm trying to make sense of all this. Because basically I'm trying to tie that to the concept of you can use phase estimation to find the energy value of of your system in chemistry simulations, in quantum chemistry, versus using the sort of the expectation So the option where you measure many times and then you average. And so in Reddit, let me just go to Reddit, because basically someone replied to one of my posts in here where I was asking a bit more about this stuff, quantum computing. And so they said something that actually, it's going to be easier if I look for it, if I go through the messages. Yeah, so this was this exactly here. So basically this person is answering saying that two of the big methods for Hamiltonian simulation include Tritterization plus quantum phase estimation and VQEs, right? So Tritterization requires QPE because we'd like to emulate a Hamiltonian H as a unitary time-dependent operator. Then we need to apply QPE to extract the eigenvalues, which are the energy values you want to minimize. But then, like, what is Tritterization? That is, so VQE differs by exploiting the linearity of matrices. We decompose our Hamiltonian into these, where H sub I are matrices easily emulated by a quantum computer, and the C sub I are coefficients. Then we can find the expectation value of H sub I, and multiply these expectation values by this, classically, to yield our energy estimate. And that's kind of what I've been seeing in the VQE videos, is that this is what it's doing. So it's basically running multiple times, kind of measuring that stuff, and then you're calculating your energy estimate this way. But I always thought that QPE, that the way it was put is that you could just use phase estimation instead of like those multiple measurements, and that's it. But it seems like that's a totally different approach. And probably opening up a door that I don't know if I might regret that. But what is Tritterization? Adiabatic quantum computation, but that's like, why would that appear? Granite Tritterization technique. Adiabatic quantum simulation using Tritterization, but that's adiabatic quantum, and I don't want I mean, what is this? Let me just check that. What is Tritterization? Hello, internet. What's up? That's what I kind of like trying to rephrase a bit. So the reason I stepped into this is because I was trying to understand what's behind quantum chemistry in that sense, and it seems this VQE, the variational approach, where you've got a where you define an ansatz. Why isn't this loading? Let me just pause that for a second. Okay, so I finally loaded. I loaded another thing. So I loaded that paper, adiabatic quantum simulation and Tritterization. But I'm not like, that's not adiabatic quantum computing what I'm looking for, because I'm looking for sort of the gate model. So, but here is like, no, wait. Here, in general, the whole Tritterized AQC protocol can be described as follows. Prepare the ground state of a Hamiltonian. Find the problem Hamiltonian HB whose ground state encodes the solution. Set the total Hamiltonian this way with slowing varying control functions, where t is the time and t is the period. Okay, then decompose the evolution operator into a sequence of steps using the Trotter-Suzuki formula, which is the key ingredient and given by these. And then this is the evolution operator from 0 to t. K is a large integer, so that finally obtain the solution by measuring the state, which is a simulation of find a small formula applies. It was introduced for the simulation of complex time-independent Hamiltonians, and the application of the formula to an adiabatic strategy involving time-dependent Hamiltonians. Yeah, but I want to know the gate model version of it. Okay, but it seems like, I don't know, maybe I'm totally wrong, but it seems like what you're doing is you're set total Hamiltonian, prepare the ground state of a Hamiltonian H0, find the problem Hamiltonian HB whose ground state encodes the solution. Whatever that means. Set the total Hamiltonian with slow varying control functions, ft and gt. So you're kind of t is a time and t is a period. Is that you're parameterizing somehow these and then evolving step by step and then trying to see how this is evolving with this time? I don't know. That all doesn't make sense to me right now. But I can't seem to find anything else in here. I'll dig a little bit deeper into this in another video, because I'll keep just working with the Cirque example as well, but I want to try to understand how the quantum phase estimation versus the VQE approach play with each other. Maybe it's just a useless investment of my time, but I feel like I want to understand that a little bit better. Cool.